Hey guys, today we're going to go over Runge-Kutta Method. But first we have to know why. And in order to do that, we have to go over the goal of the class, which you might know as, given a differential equation, we have to find y as a function of x. And there's a few ways to do that. The first of which are symbolic. That means we're taking the derivative and we're algebraically modifying it to get our y as a function of x result. Some of those were variable separable method, reverse chain rule, reverse product rule. And when that gets too complex or we can't do the symbolic method, we want to go over to the numerical, which is less of algebraically changing the derivative and more of a set procedure for finding y and constructing that. The first one we had was Euler's method, and the one we're going to go over today is Runge-Kutta, which is basically a modified Euler's method.
Recall Euler's method. Euler's method is one of the tools we can use to approximate a solution to a differential equation and or a slope field giving us differentials. Recall the formula. To find the next point, we take an initial starting point, which in this case will be when x is 0, our function is 4. Then we add the derivative at that point times our step size. So if we set our step size as 1, we're going to figure out what the point is right here. So what we can do is extend the slope at this point. And notice we're going to be taking that slope multiplied by our step size of 1, which, using Euler's method, would put us somewhere about here. And we can clearly see, given the precise solution, that we have overestimated the solution. Thus, the question becomes, how can we more accurately approximate the slope over that interval?
Okay, so Euler's method isn't the most accurate way of finding a solution in a slope field. And there are other ways, but the one that we're going to talk about today is the Runge-Kutta method. And how this works is there's an actual formula that I'll unpack for you now. If you notice, this part here is essentially the same as Euler's method, but what this part is adding is taking all of the different slopes from the initial point that you'd start at, and then kind of doing a weighted average of them to wrap our new approximation curve closer to the defined actual solution. So what I mean by that is, in Euler's method, we started at an initial point and we approximated a slope. We were fine with that, but as you can tell, there was quite a gap between the actual solution and where Euler's method led us. What the Runge-Kutta method will allow us to do is we take that initial slope plus another slope that takes about half of that height, plus another slope which is about half of that height, plus another slope, find the average of all these, and what we get is a tighter fit that comes along this solution. What these two middle terms are actually representing a trapezoidal estimation or approximation, or kind of a midpoint. So if you look at this curve here, you can draw all these trapezoids and find their area to get a better fit for this solution curve overall. So what the Runge-Kutta method is actually doing is taking an overestimate, an underestimate, and two weighted trapezoidal estimations and averaging them to get you a nicer fit to the solution curve. So earlier we unpacked what these k terms meant, but we want to kind of figure out why they're being multiplied by this 1/6. And earlier I mentioned that we're actually doing the weighted average. So if you could think of these as 6 individual objects being added together and then divided by their total. Now you might look at that and say, well, Frank, there's only 4 terms there, so why are we divided by 6? Well, if you notice, the k2 term and the k3 term are actually doubled. And this is a way of creating these terms to have more weight than the overall average of these two. Another example of that would be if I had quizzes and tests, and they were both worth 100 percentile, and you took these, and say on quiz number 1, you got a 75, and on quiz number 2, you got an 80, and then on test 1, you got a 90, and then test 2, maybe you got a 99. if I wanted to represent that these tests actually weighed more than these quizzes, I wouldn't just average all 4 of these. In fact, I may do something as simple as just doubling both sides, much like it's done in the Runge-Kutta method. So then when I did the average, I would be dividing this whole total by 6, but the overall average score that you would get at the end would be accounting for the fact that the test weighed more than the quizzes did. So looking at Runge-Kutta some more, let's talk about what some of these symbols mean. The H here is actually no different than the H found in Euler's method, which is just the overall step size. But what's really mysterious is what these K terms mean. We'll just go through them one by one. K1 is actually no different than what Euler's method is producing, which is just thinking of Euler's method as kind of an engine. It's a recursive formula where you take the initial values that you have that are either given or you created, and you feed them into the formula. It outputs a new value, and you feed that back in, and you keep going through on this. That's essentially what K1 is. It's saying, well, what is, given your differential equation, what is the Euler's method for just the one step size that you have? Moving on to K2, what you find is this trapezoidal relationship I was talking about before, which now you're actually going to take x plus half of your step size, and then the y value, similarly, is half of the step size, but it's also taking in the value of K1 and multiplying it times that overall. So once you have K1, you're able to feed that into K2, and likewise for K3, x plus 1/2 of that step size, y plus 1/2 of that step size, but this time you're going to be multiplying the y value by K2. So now you have K1, which fed into K2, which then fed into K3, and then you could take K3's value and put it into this underestimated Euler's value, which just gets you x plus h, and then y plus h times the K3 value. Once you've computed all of these, you feed them into this weighted average, come out with your new y value, and you repeat the process for as long as you need to get to your overall duration. Alright, so now we're going to use the Runge-Kutta method to actually find an approximated solution for a differential equation. What we came up with was a differential equation that equals 10x plus 2y. We have an initial value at y of 0 equals 1. We're going to use 0.5 as the step size, and we're only going to go 2 steps because there's a lot to compute by hand. So we'll basically be starting at 0, going to 0.5, and then going to 1 on the horizontal axis. So first thing we need to compute is what our K1 value will be. So considering that our initial values are 0, 1, we're going to plug that back into our original differential equation. So we'll have 10 times 0 plus 2 times 1, which then gives us 2. So now we can say that K1, otherwise known as just the normal output of our function that depends on x and y, equals 2. So K1 is 2. So starting with K1's value of 2, we can now find K2's value. And the way we do that, we're just going to plug in again this initial point that we have. So x is 0 plus 1/2 of our step size. And then we will have our value of y, which is 1, plus 1/2 our step size. And this is where we're going to use our K1 value of 2. So over here we get 0.25, and on this side get 0.25 doubled, which is 0.5, plus 1, so 1.5. So our new point for K2. Take this, put it back into the differential equation, 10 times 0.25 plus 2 times 1/2. Get our 3 here, and I don't know a quarter of that. 2.5. Gets a total of 5.5. So now we can actually come over here and say that K2 is 5.5. So now that we have K2's value, we can repeat the process to get K3's value. So starting with our initial point of 0, 1, we know that x is 0 plus 1/2 of our step size of 0.5, and then y is 1 plus 1/2 our step size, and then this time we're going to use K2's value, which is 5.5. On this side again, we get 0.25, and then over here, 0.25 times 5.5 is 1.375. So with 1, we'll get 2.375. Now we can plug that into the original differential equation. 10 times 0.25 plus our 2 times 2.375, which totals out to be
4.7.
7.25.
Just Lenny Brown it. Make sure it works.
So now that we have K3's value, we can finally find out what K4's value is. So we can take the whole average and move on to the second step. So using this initial, we know that x is 0 plus our step size. And we know that y is 1 plus our step size. But then multiply it times the value of K3, which is 7.25. Half of 7.25 is
3.75.
3.75 plus that 1. On this side we get 0.5, so we will have 0.5, 4.75. We plug this back into our original differential equation, and then we get 10 times a half plus 2 times 4.75, which all totals out to be 14.5. So our K4 value is 14.5. Now we're ready to take the weighted average of those. Now that we have the values of K1, K2, K3, and K4, we're able to find the weighted average of these in our Runge-Kutta Method formula. So what we're simply going to do is take our y initial, which is 1, plus our step size divided by 6, times K1, which is 2. Then we have 2 K2s, which is 5.5, plus 2 K3s, which is 7.25, plus our 1 K4, which is 14.5. So we're going to go ahead and add these, multiply it by this coefficient, add 1 to it to get our first step. So after computing this, we now know that y at 0.5 equals 4.5. Now we're ready to use the recursive element of our formula, put this back into it to come up with our second step.
So in the previous step, we used the Runge-Kutta method to find the value of our function at x equals 0.5, and we found that to be 4.5. Now we can use this point as our new starting point and use Runge-Kutta again to step from our 0.5 to the 1, thus completing our 2 steps. So we've already done the work here. You can see K1 is just going to be the function at that point, which is 14. K2, we're going to take that point plus half of our step size, the 0.4, and for the y component, we're going to have our 4.5y plus half the step size, a fourth, times our K1, so we bring the K1 value in. Similarly, K3, same thing, except we're going to be pulling in K2 instead of K1. Finally, with K4, we're just going to be pulling in our x value plus our step size, so we get, at the conclusion of this step, our y value is 4.5, again, plus our step size, times K3, 47.25. So, in conclusion, looking back to our formula, we bring down the initial y we started with, 4.5, plus our step size, 0.5, times all of our k values, divided by 6, remember because we have 6 elements, gives us our new y value of 18.23. And that is the value of our function at 1.